start with 12.2, 23, and we want the second edition, which, that reminds me. This is another one of those factors where the question in the second edition is different enough from the first edition, where I feel like if you did the homework in the second edition, you didn't get a full picture of things, so I think I should suggest some more problems for you guys.
What if you did first edition?
No, if you did the first edition, just don't worry about it.
Okay.
But for those of you who did the second edition, you'll probably take a look at the extra problems here over the weekend. Yeah, so if I had designed this for the second edition, then I would have probably just assigned 1 to 47 odd, except 35. So, I mean, you did some of them, but you didn't do all of them. So if you did the second edition, you'd probably want to do the extra problems over the weekend. But I won't, if you did the homework, I'll collect it now, it's fine. But yeah, we're doing 23. So what was the question? Do you have the
20, here.
Under the surface, find the volume of the given solid under the surface z equals xy.
So volume under z equals xy.
And above the triangle with vertices 1, 1, 4, 1, and 1, 2.
Like that?
Yeah.
Okay, so recall if we're looking at this.
Problem 19. Yeah, that's 23.
This is actually 19 in the first edition. Okay. So remember this guy, you can think of as the volume under F over the region D. That's one way you can interpret this integral. Just like how back in Calc 2 you could interpret integration as finding an area, you can interpret like a double integral as finding a volume. All right, so this really gives you the net volume under, right? So basically we're going to use an integration here, and it's over the region D. So you're always going to want to figure out the region D, and notice that the limits of your integral describe this guy. Right, so that's one of the main goals in setting up the integral, right? So once you can describe your x as an inequality, it goes between this and that, and the y goes between this and that. Those are the guys you put on the integral, right? So just want to make sure I keep emphasizing that. Okay, so here we first have to figure out what the d looks like, because that's going to tell us what limits we have to put on the integral. So let's actually figure out what this guy looks like. So we're going to do 1, 1 here. I can do 4, 1 there, and then 1, 2. Right? So this is my region D. Okay, for this particular problem. So now we have to describe that using inequalities. How would we do it? Yeah?
You can describe it x being between 1 and 4.
Sure.
And then you can describe y as a line.
Y is a line. So you'd have to find the equation of this line, right? And y would go from 1 up to that line, right? So we know that the lower limit here is 1. But what is that line?
Negative 1/3 x plus 7/3.
Or
So this is y equals minus 1/3 x plus 7/3.
or 7 minus 3, right? Or x equals 7 minus 3.
Yeah, you could do that also. Or x equals 7 minus 3y. Okay, so which one would you try to set up? I'd probably go with the one that doesn't give me fractions, but maybe that's just a personal choice. Okay. So you could also actually let the x go between functions if you wanted. So you can say x goes from left is 1, the right would be 7 minus 3y, and then y goes from 1 up to 2. So I could have done that. The volume is going to be given by 1 up to 2, 1 up to 7 minus 3y of xy dx dy. That would be the setup, right? This is equivalent to x goes from 1 to 4, y goes from 1 up to minus 1/3 x plus 7/3 xy dy dx. Right? So either one of those, if you set the whole thing, you should get the answer. Okay, so now let's continue. Let's evaluate this one. The one without the fractions. Okay, so x, we integrate that. This becomes x squared over 2y between 1 and 7 minus 3y. This is y times 7 minus 3y squared over 2. Minus, I plug in 1 for the x, so this is just y over 2. Y, because I took out the half. And I mean, the rest of this is just, it's a single variable integral now. It's just a matter. This is 49, 3, 7, 21 times 2. So 2y plus 9 squared minus y. So this is going to be 49y minus y, that's 48y minus 42y squared plus 9y cubed. And what was the answer for that?
31/8.
It's calc2. Got 1 even. Okay. But the hard part was, I think, would be the setup, right? To figure out how to actually set this up. So one of the ways it's going to be really convenient is first being able to draw the region, which is why we taught you how to draw quadratic surfaces. Eventually we're going to come to a point where we're integrating on surfaces and things like that. So drawing is a very important thing. Having the picture is going to tell you how to do this, right? Because it helps you to set up your limits properly. Once you have that, then it's just a mechanical thing. Second edition? Huh?
Yes.
What does it say?
Find the volume by subtracting 2.
Okay, so what is the volume you want?
So there's y equals 1 minus, well, it's bounded, it's in the bounded by 5.
Yeah, tell me how it's bounded.
So y equals 1 minus x squared, y equals x squared minus 1.
It says bounded by,
Y equals 1 minus x squared, and then y equals x squared minus 1, and planes x plus y plus z equals 2, and 2x plus 2y minus z plus 10 equals 0.
minus z.
Plus 10 equals 0.
Okay, so how would we actually do this one?
Try to graph this.
Try to draw a picture, right? So we know that these two here are going to be describing the region. So we have two planes. We have the plane z equals 2 minus x minus y. We also have the plane z equals 2x plus 2y. That's 10. Now if you were to draw this guy, if you're drawing plane 1, remember you plug in x and y equals 0, you would get z equals 2. plug in y and z equals 0, you get x equals 2. Plug in z and x equals 0, you get y equals 2. So that's that plane here. Here, plug in x and y equals 0, you actually get z equals 10. Plug in y and z equals 0, you get x equals 5. X equals minus 5. It's there. And if you plug in y would also be minus 5. Okay. So you can see here, and if we're looking at these guys, 1 minus x squared in the xy plane, that would be something like this. We don't want to actually right here. And x squared minus 1 would be like that. Notice though that what you really want to get at here is you want to have some ideas of who's on the top and who's on the bottom. That's what they mean, subtract one volume from the other one. When you're over this region, this plane, the one with the 10 in it, is actually above the one with the 2. Right? You can see that. Like this one is slanting up over here, this one is slanting under there. So what you should get from this is that this is the top and that's the bottom.
So we should really draw.
In other words, the volume is going to be given by the volume under this minus the volume under that. And our graphs, which there are a lot of surfaces going on here. I mean, you can't really draw it by hand to like really see it, but. Okay, so let's do that. So the volume is really going to be. Now let's set up the region. Let's put 2y plus 10 minus 2 minus x minus y and 8. Now the region D, well that's given by these two guys that they gave us, 1 minus x squared and x squared minus 1. That's your D, so this is y equals x squared minus 1, so this goes down to minus 1. This guy is y equals 1 minus x squared, so this goes up to 1. How would you describe the region?
By the intercept, I think.
Right, the intercept they'll intercept at the same place, right? Where is that?
X is between -1 and 1, and y is between x squared minus 1, x squared plus 1.
Right, so your top function here is actually the 1 minus x squared. Your bottom function is the x squared minus 1. And then here you'd have 2x plus x, 2y plus y, 10 minus 2. So that would actually be the setup. Now it's just a matter of development. So this is here you intercept to y first, so we have 3xy plus 0/2y squared plus 8y. Now, 1 minus x squared squared and x squared minus 1 squared, they're actually the same thing, right? So this will actually kill that. And then, now we just multiply these guys out, see what we get. So there's going to be a lot of guys dying here. So this is 3x minus 3x cubed plus 8 minus 8x squared minus 3x cubed plus 3x minus 8x squared plus 8. Did anyone die or did they just doubled up? So we have minus 3x cubed minus 3x cubed. Minus 8x squared minus 8x squared. And I have 3x plus 3x. I have 8 plus 8. And that should give you the other ones. So we want to continue this. So here we would have minus 3 over 2x to the fourth minus 16 over 3x cubed plus 3x squared plus 16x between minus 1 and 1. So that's going to be minus 3 over 2 minus 16 over 3 plus 3 plus 16 minus 3 over 2. This would be plus 16 over 3. This would be plug in minus 1 here, so this is plus 3. Plug in minus 1 here, this is minus 16. Okay, so these guys die. And so we just get 16 minus a minus 16. Putting it here. So it's 32 minus 16 over 3 minus another 16 over 3. So I'm minusing 2 16 over 3s, which is 32 over 3. So this is just 64. Other questions? .3 maybe?
About 21 in the first position.
And 27 also?
We're 29.
And you was 29.
What is 21?
You said first.
Oh, yeah, so this is just one loop of the rows R equals cosine of R.
27.
Oh, well, we did,
We did something similar.
I did a similar example to that in class yesterday.
Oh, the. Yeah,
Use a double integral to find blah.
Had trouble drawing the rows and figuring out what all the angles were.
Oh, to actually draw it? I mean,
yeah, drawing first.
well, technically you just have to find where it's 0. That's tell you where all the loops are. I Okay, so we want one loop. You can draw it if you'd like, but one loop of r equals cosine 3. So first, set cosine 3 theta equals 0. This means that, how do you solve that? Cosine 3 theta equals 0. What are the values?
So 3 theta equals 0 or 3 theta?
No?
No.
Cosine 0 is 1.
Oh,
Where's cosine
pi
equals
over
0?
2, negative pi over 2.
It's n pi over 2 where n is odd, right? That's where everywhere where cosine is 0. So then your theta looks like n pi over 6 where n is odd, right? So that will be, in the between 0 and 2 pi, that would be pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, right? 1 pi over 6, then the next one is 3 pi over 6,
Okay.
which is pi over 2. The next one would be 5 pi over 6. Then the next one would be what? 7 pi over 6. You'd have 9 pi over 6. And 11 pi over 6. Those are all of them between 0 and 2 pi, right? Now, if you're actually graphing this guy, the first thing you'd want to do is to graph r versus theta. Right? In which case, you know that cosine, the amplitude is 1, right? Because the coefficient is 1. We know that the period is, well, you'd have to remember how to draw trig graphs. So you remember that if you have y is equal to a sine k x minus b plus c, or a cosine k x minus b plus c, then absolute value of a is the amplitude. That's how high you go up or down from the middle position. B is called the phase shift, which is a horizontal shift. C is the vertical shift. If you take 2 pi divided by the absolute value of k, that gives you the period. Right? So here, our k is 3. Take 2 pi over 3, right? So here, the period is 2 pi over 3, right? Which means there are a third of 2 pi. So if I put here 2 pi, split that into 3. 2 pi over 3 is the period of one whole graph here. Right? So for that, I have a cosine happening in that region. Right? And of course, if this is 2 pi over 3, then I just divide it into 4 to get what each of these are. But I actually know where all these zeros are. These are the guys I found. So this is actually your pi over 6, your pi over 2, etc. Right? You can actually find the value. There's also something called the subinterval, which is just the period over 4. Because you know sine and cosine come into 4 sections. So you can find all these important points that you need. But the important thing is to realize that a loop happens when you start at 0 and you come back to 0.
Okay, and so I can choose any.
So you can choose
of those
any
states.
pair of these angles, right? I mean, you don't even need the polar graph. I mean, it'll look like a flower.
Right, yeah.
But
You're gonna ask something like this in the test?
no. But you wouldn't need the picture for this. I'm just showing you, if you wanted to draw it, that's how you would do it. But I wouldn't ask you to draw this. No, that's calc 2. But what you would know is that you had to find the zeros. A loop happens when you go from the origin, you go somewhere, and then you come back to the origin, right? So all you had to do, you didn't need the picture here, just find out where it's 0. And then you know between this and that is going to be, you know, a loop. So you can pick any 2 points you'd like. So I can go from, say, pi over 6 to pi over 2, and that would work. So the area can do theta go from pi over 6 to pi over 2. R is going from 0 to cosine 3 theta. Or I can even do the first one and double it, because that would be nice. Notice that here I have a half loop from 0 to pi over 6. So I can do 0 to pi over 6, double the answer, and then I integrate the function 1 times r d theta. This gives me r squared over 2 times 0 cosine 3 theta.
Wait, why times by 2?
Oh, I split it, right? I'm using the first one, 0 to pi over 6. Notice that only gives me half a leaf. Right, so then I would have cosine 3 theta squared over 2, which would kill this. And then that's just 1/2 times 1 plus cosine 6 theta. That's going to be theta plus, well, this is going to be 0 anyway, but whatever. Cosine sine 6 theta between 0 and pi over 6. Now this guy's going to give you 0 in either case, so we just have pi over 6 times 1/2. Another question?
Number 19,
You're in the first edition or
the
second?
second.
So what does 19 say?
It's evaluate the double integral of 2x minus y of d bounded
Sorry about that. That's so number 19.
Yes.
Oh, so we want to do the double integral over d of 2x minus y dA. D is the disk at origin with radius 2. Do you have the first edition or the second edition?
I have the second edition. Did I give you 12.2?
Okay,
Yeah.
give me that was 12.2. Not the wrong edition, it's the wrong section. Okay, 19. So we want use polar coordinates to find the volume of the given solid, right? So we want the volume inside both x squared plus y squared equals 4 and 4x squared plus 4y squared plus z squared equals 64. Okay, so how do we find that? So notice first the picture, what would it look like? It would be an ellipsoid, it would look like this. It would be elongated like against the z, and then you're having a... What would be the radius over here?
4.
Hmm?
For what? No, I'm sorry? 4.
For the ellipsoid?
That's 4.
It's 4? How did you know it's 4? Well, you can go from here, right? You divide both sides by 64, right? So this is x squared over 16 plus y squared over 16 plus z squared over 64 equals 1. So we know it goes up on z to the 8 and it goes here to the 4s. Then there's another cylinder on the inside. That has radius 2. So I want the volume inside both. It means I want the volume of this guy here. Okay. One thing you could notice is that I can actually do the volume from 0 and above and double it if you want to use symmetry so that you have zeros to help you out. It's less hassle. But you can do it either way. So in this case then, what is our region D?
Cylinder. Circle.
Which one?
X squared and y squared equal 4, so it's 2.
Yeah. So you always want to know what you're integrating over, because that's going to be the limits on your integral, right? X squared plus y squared equals 4, right? So that's the region D, which means in polar coordinates, we actually know how to set that up, right?
It's just x squared.
So we decide r and theta. R goes from 0 to 2, theta goes from 0 to 2 pi. Okay, so those are the limits on our integral that we get from the region that we're integrating over. Right? And so now the volume, I can just equal 2 times volume above xy plane, which is just 2 times the double integral. Theta goes from 0 to 2 pi. R goes from 0 to 2 of something r dr d theta. Now what is the something?
Ellipsoid.
Right. So remember, if I'm finding the volume here, it's the top minus the bottom. The bottom is 0, so it's just the top, which is the ellipsoid, right? And the ellipsoid I can actually write here. I can solve for z, it's going to be the square root of 64 minus 4 x squared plus y squared. Right? So this I can write as the radical of 64 minus 4 r squared. And that will actually give me the volume. The cylinder gave us D. If you notice that it was what defined where I'm integrating, right? That I'm integrating inside that cylinder. Right, so that's where it's usefulness. Okay. And so now, how do you integrate that?
Take the 4R.
You could factor a 4 out, sure. This would be 4. But that just makes it just a very small.
Just do a use of.
Yeah, just do a use of. So.
The inside of this goes.
Yeah, so you can set u is equal to 16 minus r squared. Du would be equal to almost r. Minus 1/2 du is equal to r dr. And this is optional, but you could change the limits if you wanted. When r equals 2, then u would be 16 minus 2 squared, that's 16 minus 4. And when r equals 0, your u would be 16. So this is 4 times the integral from 0 to 2 pi times the integral from 16 up to 12 of minus 1/2, I can bring out here. So this is minus 2 of u to the 1/2 du d theta. So that becomes, add 1 to the power, you get 2, u to the 3 over 2 times 2/3, right? So it's minus 4 over 3 times, this integral is going to give you a 2 pi, let's just get that out of the way. And this is going to be 16 and 12. So then it's minus 4/3, well, minus 8 pi over 3 times 12 to the 3 over 2 plus 8 pi over 3 times 16 to 3. I don't know how much they simplified that. Did they simplify that much? I don't know. Not much. I mean, you could factor out the 8 pi over 3 and take 16 to the 3 over 2 minus 12 to the 3 over 2. That'll be fine too. Right? Although you could take the square root of 16, that would be 4 cubed. And then, yes?
Oh, so with the 2 pi, you just, you didn't have to integrate it, you just saw that it was.
No, because the integral of this doesn't have any thetas in it. That would just be a constant, right? And so then it would just be theta and then plug in the 2 pi. Yeah, because this never depended, the R integral depended on theta none at all, right? Theta was not in the function or in the limits, right? If it's in either one, then I couldn't have done that. Other questions?
Yeah, number 27,
Second edition, right?
second edition.
Okay, a swimming pool is circular, 40 feet diameter, the depth is constant. Linearly from. Okay, so. So that's sort of your swimming pool, right? It's circular, but at this base, the height is 2, and over here, the height is 7.
Wouldn't it go the other way if it were a swimming pool?
What?
It'd lose all its water. Sorry.
That would be 2, that would be 7, and that's in the north direction. So how I'd probably set that up is to probably put this right in the axes, right? Sort of make the y-axis point north, the x-axis points east, z-axis points here, and then sort of figure out what the guy has to look at. Well, it depends if I want the pool, I can make this like at the ground level or something like that, you could do that. So now we're just going to have to figure out, so obviously the volume is going to be, we're going to be integrating over that circle, right? But then the top surface is going to be a flat plane, the bottom surface is going to be a slant plane. So now you just have to figure out the equations of these planes. Let's say I made the origin here. That's 0, 0, 0. What would this coordinate be? What would this coordinate be?
0. I don't know what it would be on the other side.
That's 20.
0, it would be, for the y, what would the y value be?
Negative 20. Because 40 for the diameter.
What's the diameter is 40, right, so it's minus 20, and the z is still 0. point here would be, I mean, this plane we already know is the plane z equals 0. So, and this would be 0, 20, 0. This point here, though, would be what? That's going to be the
Negative
important
2.
one. What's negative 2? X is still 0. The y is still minus 20. The z is minus 2.
Right.
Right? Here, x is still 0, y is still 20. The z is minus 7. Right?
Right.
So all I need is like a flat plane that passes through these 2 points. Right? But I know that the x is constant, so my plane only has y and z in it. Right? Because it says it's constant from the east-west direction. So along the x, it's not moving. Right? So since the plane is constant in x direction, its equation only has y and z. So now I just have to find the equation with y and z. Now I can just find the equation of a line in y and z, and that would be good enough. Right? So if I look at it like yz equals y1 z1 equals minus 20 minus 2, y2 z2 equals 20 comma minus 7. What's the equation of the line hitting those 2 points? First we find the slope, right? So it's z2 minus z1 over y2 minus y1. Right, so that would give you, what, minus 5 over 40? So then it is z minus z1 equals m y minus y1. So that's actually the equation of your plane. So then the volume is going to be given by the double integral over d of the top, which is 0, minus the bottom surface, which is going to be z equals minus 1/8 y. This is minus a quarter, minus 2. That's what? What do you say? That's what? That's 9 over 4? Right, because this is minus 1/4 minus 8 quarters. Okay, so then it's minus 1/8 y minus 9 over 4 dA, which is just the double integral over d of 1 over 8 y plus 9 over 4 dA. So now I want to set this up with polar coordinates, obviously, because we have a circle. So we know the circle, it's obviously 0 to 2 pi. What's this guy here?
0 to 20.
0 to 20, right? R goes from 0 to 20, that's the radius. What is y?
R.
Y sine theta. And this is r dr d theta. Now in this case, I can't just put that 2 pi on the outside because I have something that depends on theta here. Right, so I'm just going to have to do the integral in the regular way. So this, we're going to actually integrate with respect to r first. So this is really 1 over 24 r cubed plus 1 over 8 r squared. And then, so this would be 1 over 24 20 cubed sine theta minus 9 over 8 times 20 squared between 0 and 2 pi theta. But remember, sine will give you 0, so you just ignore that part. It's a plus. And so we have 9 over 8 20 squared times 2 pi. This is that 4 times, this is 9 over 4, 20 squared is what, 400?
I have a question.
Yeah?
Why did you cross the sign? Like, isn't it gonna turn into cosine when you integrate it?
If you have 0 to 2 pi of sine theta d theta, it's 0. Same thing with cosine. Right? Anytime you're integrating over a multiple of the full period, you always get 0. Because there's going to be a top part and the bottom part, they kill each other with sine and cosine. If it wasn't 0 to pi or not a multiple of length 2 pi, then I'd have to actually do it. But I can ignore it. Other questions?
Yeah, 29.
Hmm?
29, second edition.
29. That's actually a good problem. I wouldn't really ask it, but it's one that really gets you to think about the concepts of what it means to set up a limit, so it's a good problem in that case. So they want to find that of xy dy dx plus okay, so use polar coordinates to combine the sum into one double integral and evaluate it. Right, so first let's regions. Okay. What region does this describe? Describe the region to me.
It's part of an eighth of a circle. Slice.
How would it look? What does this look like? Semicircle of radius 1, right? Okay, x is like this. And then they're saying my x goes from, it goes up to 1, but it goes down to 1 over radical 2, right? Where is 1 over radical 2 here? It's where it actually intersects, right? So this is actually describing this region. Right?
No.
No? It's one of what? No, what's not?
X.
Y goes from, right, that's not the right one, right? What was wrong with that? This is the bottom,
Yeah, that's correct.
right? X is the top.
Yes.
That. Now, what is this region describing? Again, there's the function x. Then there's the function x goes from, y goes from 0 to x. X goes from actually radical 2. It goes from 1 up to radical 2, right? So that describes this one, this region here. Right? What does this describe? What's this guy?
Circle radius 2.
Semicircle with radius 2, right? So y goes from 0 to that, but then I just let the x goes from radical 2 up to that. So this is the region that describes. Now, you can combine them all into one region, right? If I actually take this, attach it to that, attach it to this, what do I actually look like? Notice here, circle radius 1, here, circle radius 2, I have x going through the middle. Here is, this intersection is 1 over radical 2. In the middle I have radical 2, which is actually that intersection. So the first integral says that we should integrate where? The first integral said integrate this part. Then the second integral says integrate this part. Then the last integral says integrate this part. At the end of the day, your region of integration is just this. What's the angle here? Higher force, half of 90 degrees, right? So you can actually just, when you look at, remember that this was the thing I was talking about, integrating over several regions, right? If you break up a region, D1, D2, D3, right? Then the integral over the whole region is equal to the integral of the sum of the each pieces, right? So that's sort of what this problem is telling you. But you had to figure out, this describes that, this describes that, this describes that, but I can actually put them together to form a region where polar coordinates would actually work really nicely on. So at the end of the day, so we get theta goes from 0 to pi over 4, r goes from 1 up to 2, of x times y, which is going to be r squared sine theta cosine theta, times r dr d theta. All right, this is your xy. And so that's the integral you want to compute. And it's actually the same as doing those 3 double integrals and adding them together. So, and we can do that. So this is r cubed over 3. So I plug in 2 for the r. I get 8 over 6 minus 1 over 6. So that's 7 over 6. Sine 2 theta. So then this becomes 7 over 12 sine 2 theta between 0 and pi over 4.
It's not right.
Huh?
I lost the R in the seconds. You lost the R.
Where?
The R square. It's R cube. You just put R square and you integrate.
Multiply the r.
Oh, this is
Yeah,
r
R
cubed,
before,
so it'll
yeah,
be r, right, it's r4 over 4. So this would be 8. So that would be 16 over 8 minus 1 over 8.
I think it's cosine 2. Cosine 2 theta. I think it's cosine 2 theta. It's not sine.
Yeah, I was talking about this part, right? That's right so far now, right? 15 over 8 times cosine, and we plug in cosine, what would this be?
Over 16.
Negative 15 over 8.
No. 15 volts. This should be voltage. 16,
What do you,
15 or 16.
yeah, that's what I got.
50.
I mean, for 12.4,
This should be positive.
we won't have a lot of info. This is basically uniform.
It is positive. Because integral sign, yeah, it has to be positive.
Huh?
It's
What?
This should be positive.
Yeah, it's not positive.
Should it be positive?
Well,
Same
where did you get the
theta.
8 from?
Sin
So-
to theta
R
should be
over-
cosine to theta. In
The-
the second term.
R to the 4th? Where did you get the 8 from? Shouldn't that be R to the 4th over 4?
No, you do the integral for the sine 2 theta,
It
you
should
got
be
R.
cosine to theta.
No, I use that sine theta, cosine theta is actually a half sine 2 theta.
Yeah. But when you
So I use that
partial
here.
integrate, so it should be cosine to
So
theta.
this would be r cubed times 1/2 that, right? So that goes to r to the 4th over 4 times the half.
But it should
is
be
this.
cosine to theta after your
I didn't do
integration.
that.
This should be cosine to theta. In the second process, in second step,
I don't know.
in the second step, it should be cosine to theta. Yeah.
Well,
Right?
I kept it as cosine theta, sine theta, and got,
Cosine on the bottom.
Yeah, it's negative cosine to theta. In the second step.
Right here?
Yeah. Yeah, yeah.
Oh, yes. Okay, yeah. Okay.
No, I mean there. In the second. Yeah.
Well, yeah.
Where?
the second line.
Yeah, yeah.
Sine to-
This one should be cosine to theta. Minus. Right?
Oh, I didn't integrate the theta yet.
Oh, yeah?
Here I just integrated the r, so that's fine. I integrated this here,
Yeah.
which would make this
16.
16. Right.
Yeah, it's
Yeah. Stop confusing me with your accent. Maybe one more question. Make it a good one. Because that was a good one. Right, you can sort of see the relationship between like an integral, and you can actually tell where you're integrating, right? You should learn how to read these limits really well. And of course go vice versa, right? You should know how to go from the limits and to the picture, or from the picture to the limits. Because you'll need to know both of them. Like if when you're switching the order of integration, you need to know to go this direction. If you're setting up an integral, you'll need to go in that direction. So you should know how to go from one to the other. Okay, other questions? What? Number 7 in the second edition. Evaluate the integral by changing it to polar coordinates. D is up at of this. Right. Center, the origin, radius 5. Okay, how do we set that up?
So it's half circle.
Yeah, top half. So D looks like this. So R and theta. What is R? And theta is 0 to pi, not 2 pi. And then, so theta goes from 0 to pi, R goes from 0 to 5. You'd replace this with R x worth R cosine theta, so at the end is R cubed cosine squared theta sine theta, R d theta. This is R to the 5th over 5. So this just becomes 5 to the 4th between 0 and pi cosine squared theta sine theta. So then you're going to integrate this, and you're going to have minus cosine p theta over 3. So cosine of pi is minus 1, so that gives me this. Minus. Cosine of 0 is 1. So then you get 2 times 5 to the 4 over 3. I don't know, whatever that is. What's 5 to the 4? Okay, we're done. So now because of Bishoy, which is the guy right there in the green shirt, we have to do a quiz. He forced me to make one even though I didn't want to.
I think we could just flog him instead. Right? Don't we all agree?
I'm kidding. We only have 2 weeks left.
You
I
don't
get
want
to
to waste
show on the
time on a
road.
quiz. Yay, we win. Are we passing homework?
Yeah, pass up your homeworks.
Was that great or what?
What?
Nothing.
What? What was the grade?
I did a problem and got the right answer with the wrong approach again. Come on, you
Stop
should
using your
be
secret
proud of
weapons.
me. You should be proud of me. Here.
Okay, as far as 2.4 is concerned, there's no real new theory on integration itself. They're just doing applications. We were just going to look at one. it's called the center of mass. Right? So remember, we actually did that in Calc 2. And we had, the formulas actually look very similar. Suppose center of mass and mass and center. It should be the other way around. Suppose we have
There was a section about somebody else.
So basically what we have here is just, this thing can have any shape it wants. But let's say you put it in space. Has some negligible thickness, but it has some other area properties here. And we know the density at any point on this solid is given by some function, right? Let's say you know how to find the density at any point, right? You can actually find the mass that it holds and the center of mass, which is the point where you'll actually be able to balance the solid, theoretically. It's not always on the object itself, right? So we actually did this in Calc 2, and the formulas here look pretty similar, except now they're all double integrals. That's pretty much it. So if you integrate density, you get the mass, right? Where D is just the region of projection of this thing. Zero density is the mass. Also, there are things called mx and my, which is the moments are on x and the moments are on y, and that is given by y times this guy. A and y d by x times this guy. Also, define x bar to be 1 over m times m. Basically it. So if you integrate the density, you get the mass, and if you figure out the moments about x and y, you can get to the center of mass by doing this equation. That's sort of it. Okay. This can work in higher dimensions also. So let's say now you're still in 3 dimensions, but now you have an object whose thickness actually matters. 3-dimensional object. You can still figure out where its region of projection is. Call this solid E. Right, so here we know for any random point x, y, z here in this object, rho of x, y, z equals the density of the object. At the point x, y, z.
What do you mean by thickness? What do you mean by thickness?
Like the distance of the z values, the distance between the z values. Well, that's sort of how I'm setting it up here, but it could be either way. Right. Just like if you have a rectangular box, you know, you can do length times width times height, and you should say the thickness is the height, or you could define it to be this. Or this. It sort of depends on how you're looking at it.
What is that?
But in the first, what?
What is that point next to the E?
This is just the point x, y, z.
Oh, okay.
I just called it, or I picked a random point in the object, x, y, z. And I know that the density at that point is given by this function, rho of x, y, z. Then you actually can do these integrals to figure out the center of mass and the mass. Now what do you notice about these integrals? They're triple. 12.5, triple integrals.
Well, that was fast.
No, you're not needing examples.
Are you sure?
I'm positive.
Moving right along.
Of course you have to do the homework.
Do you want an action question?
Yes.
So why is there no Z bar?
For, I put it up here. Really, as far as integrals go, 12.4 has no new theories. Basically just knowing these formulas and applying them. So you set up the integral the same old way and everything's done
And it's
exactly the
same
same.
inside to outside and.
So everything else is the same. You're just using formulas now. That's it. Really.
So if you give us a quiz, it's gonna be everything till 12.
Of course. Everything. That's in a record.
It'll be like a mini test.
I mean, you'll see when you do the homework for this. You'll see it's just setting it up and it will be fine.
You have such confidence in us.
Of course. You know, class average is like a 80 something. Of course,
It's because two people knock it up.
Yeah, we know who is to blame. Yeah, okay. Let's look at the basics.
The rest of this was below the curve.
Okay. Let's start with the equivalent of 12.1. So recall in 12.1 we integrated over rectangles. Right, so triple integrals are very similar to double integrals, just everything is one higher dimension. Right, so rectangles are now we think of them as boxes. Right? So let's call P the object, which I described as AB, CD, IEF. That's just the set of all points x, y, z, such that the x is between A and B, the y is between C and D, and the z is between E and F. Then, triple integral over E of the three-variable function fyz dv. Your V here stands for volume, right? Just like dA stood for area, because your region was a two-dimensional thing. For triple integrals, your region is a three-dimensional thing, so we think of it as volume. So we use dV to be the generic differential. That's just going to be equal to x dy. And if f is continuous, so just like back in 12.1, if you had constants on your integrals, you could just switch the integrals and switch the order of integration, no problem, right? It's when there are non-constant limits that things are trouble. can have trouble. Let's do an example. Let E be interval x, y, z such that x is between 0 and 1, y is between 0 and 2, z is between 0 and 1. I do the Riemann sums for you, but I can't draw rectangles in the fourth dimension, so that's sort of, that would really be. Yeah. So again, this is sort of the physical quote-unquote interpretation is this is finding a hypervolume, right? The hypervolume in the fourth dimension under this surface. It's sort of weird to think about. But we can actually.
What's the limit for z?
Yeah.
0 and 1.
0 to 1. X is between 0 and 1, y is between 0 and 2, and z is between 0 and 1.
So how would you best describe a hyperbolic?
I don't know.
Like, is there any sort of visual or?
Not
Watch some Stephen Hawking movie.
Like some vortex or?
So does this mean we're skipping
Visual.
13.6?
Come again?
Are we skipping 13.6?
I want to do 13.6 after this.
Oh.
After this section.
How about 12.4?
We did that.
We did talk. Yeah, it was
You
fast.
blinked.
So, yeah. Must have blinked and missed it, yeah.
That was the center of gravity thing.
Center of mass was 12.
Center of mass.
Which is just formless. Okay, so I just have that example. Okay, so let's actually do that integral. What does this look like?
I don't know. It's in the fourth dimension.
It looks like the event horizon of a black hole. As we get sucked and pulled to pieces again.
Okay, so how would you set that up?
0 to 1, 0 to 2, 0 to 1.
0 to 1, 0 to 2, 0 to 1. Really doesn't matter the order. This is continuous and these are constants, so you can really do it any which way you please. So this I can do dx, dy, dz. dz, dy, dx could also work for the same thing. So how do you do a triple integral? Same thing applies. You work from the inside and you do it outside. So 0 to 1, 0 to 2. Here, integrate with respect to x, x cubed over 3, y, z, between 0 and 1. That gives you a third. 0 to 1, 0 to 2, y, z, z, and do this inside. Integrate y, you get y squared over 2, so this becomes 1 over 6, y squared, and 0 and 2. And you put in 2, that becomes 4, so this becomes 2/3, then 0 to 1, z, dz. So, I mean, not much difference, you just do an extra of integration. That's fine. Now let's go to the non-rectangular regions. So again, your book describes this one in 3 types. So back for double integrals, we have 2 types. Now in triple integrals, we have 3 types. I don't care if you know what type refers to what, just recognize how to set one up in each case. Right? So your book calls this one type 1, and that's the one where your part of your double integral is in the xy plane. So there's a type 1 region. This is where you think of your region of projection being in the xy plane. So here I have f1 of xy. On the bottom I can have 2. Well, I usually call 2 it's off 1 to 1. Here, your object E is described in the following way: the set of all points such that Z goes between F1 and F2. And XY is so the triple integral over E of f of x y z dv is going to be equal to the following. You're going to have the double integral over D, and inside you're going to have the third integral, which goes from f1 of xy up to f2 of xy. Now, one thing to emphasize here is that your 2 outer integrals are just like your double integral setup, right? So the 2 outer integrals describe your region of projection, right? Now, once you're in this region of projection, you set it up just like a double integral, right? You try to find a constant to bound one set of variables and a functions to bound the other set, right? Now, depending on what this region looks like, you might set it up one way or the other. Right, so this you can set up as a dx dy or dy dx, whichever one is convenient. You can also set it up as in polar coordinates, which comes in the next section, but we'll get to that. We'll cross that bridge when we get to it. Right? So the idea is you can think of your object as being bounded between 2 surfaces, and you're projecting in the xy plane. In that case, you would set it up this way, right? Where you think of the surfaces that your z is bounded by, put those on an integral. And then on the outside, you just do the double integral setup for that region of projection, which you'll be able to figure out based on what the information you're given. Just how to sort of think about it. Let's say you have some sort of object. It's projected into here. D. So first you'd have to figure out what the object looks like and figure out what its shadow looks like. Then, suppose you could have its shadow, you can describe it in this way. Where you have G2 of x, G1 of x. And this is in the xy plane. here, your top surface is given by f2 of xy, your bottom surface is given by f1 of xy. And let's say your limits on your x is from A up to B, right? So I give you enough information to actually draw this object, which by now you know how to draw a bunch of objects. Then you're going to figure out what does the region of projection look like. Then that one you're going to dissect into your constants and your functions. And then you'd be able to actually do an integral, right? You'd say the triple integral of f dv over E. That would look like, how would this integral look? So on the inside, just follow the surfaces for this guy, right? So it's f1 of xy up to f2 of xy. Now what does the outside look like?
G2
G1 of x up to G2 of x. That's, so this was dz, this will be dy, right? Y goes from this function to that function. And x goes from this constant to that constant. Right? So you figure out this and you look at its shadow. The shadow is going to tell you how to set up the x and y on the outer integral, just like double integrals from previously. Right? The last integral is just going to be the different surfaces. Right? So there's going to be a top surface and a bottom surface, and etc. So here we add that constant, right? Constant, bottom surface, bottom curve, top curve, bottom surface, top surface. One thing to notice that these are constants. Again, with triple integrals, constants always on the outside. Constants, these are zero dimensional, which are just constants. These guys here, these are actually single variable functions. Would go in your inner integral, right? This one, so these guys are two-dimensional. Here, these are two variable functions would go here. So these are one-dimensional. So you can have up to two variables on this integral, only one variable on this integral, only constants on this integral, right? You go up by the dimension, the more you go in, right? So we could do 4 integrals, where this integral here, we have 3 variables on it. It would be in 3 dimensions, etc. But for triple integrals, that's what it should look like, right? So conceptually, this is the kind of thing you're setting up. Figure out what surfaces bound your thing, then what curves bound the shadow, then what constants bound the other dimension of the shadow. Type 2 and type 3 are very similar. I'm going to write them down, and then we'll do some examples. What happened? We also have type 2. Now type 2, they call it when they're projecting the YZ plane. I don't care if you know what they call it, it's just this textbook calls it down. So that's when you look at things here. D is projection in the YZ plane. And this is x1 of YZ, x2 of YZ, this is f, and then this is dx. dA. Here your dA is either dy dz or dz dy. Right? Wherever your projection is, those are the variables that you're integrating. So an object like that would look like this is x2, so if you're thinking of your thing as bounding between a left surface and a right surface and you're projecting into the YZ plane, that's a type 2. In which case your outer integrals describe what's going on in the YZ plane. Your inner integral describes the surfaces in terms of y and z. Here, there's also type 3, which is obviously projection in the other surface. So type 3 is y1, z, 2, z. This guy b dx dz or dz dx. So in this case, your solid could be described as the set of all points such that so the theory, it's sort of hard to see, but we'll do an example now so you should sort of get it. to evaluate as type 1 and set up type 2 and 3. How this look as type 1? Could we actually draw the region?
Yeah.
How would it look? What?
You ever played D&D? Four-sided die?
Things like that, right? Well, they're all equal. 1, 1, and 1 is where it intersects, and this is the tetrahedron, right? The YZ plane is one side, XZ plane is one side, XY plane is one side, and then this plane forms the fourth side. And type 1, it means our region of projection is in the XY plane. So I'm thinking of this as the projection, right? That's D. Okay? Which means for my region D, it's just this guy in the XY plane. Right? Just a straight line that connects 1 and 1. Which means I can describe D as what? I can let X go from 0 to 1. Okay, and then the Y would be what? Huh? 0 to 1 minus X, right? You find the equation of this line. This is Y equals 1 minus X. So it means that guy is the region D. Also, here, how could I set up my Z range? Z would go from 0, which is the floor, right? Z equals 0, up to what? 0 up to the plane, right? The plane is the roof, it's the top here, right? And the plane is going to be Z equals 1 minus X minus Y. So what this integral looks like X, 0 to 1 minus X minus Y of the function 1 dz dy dx. Right? So this is the bottom surface, the bottom curve, top curve, the left constant, the right constant. Right? So notice that these two out here was just like setting up a double integral for the region of projection. Right? So the same thing we were doing in 12.2, 12.3, that's what you're doing here. For the third integral, you're looking at the surfaces now, right? Where's the bottom surface and the top surface? Here it was 0, the top was the plane. And then we have here. So notice that here, your third integral towards the inside has two variables on it, x and y, right? If you had two variables over here and one variable over there, you did something wrong, right? Can't happen, right? Two variables here, one variable here, constants here. That's how it should look. Right? You could have constants everywhere, but if you have variables, this can have at most two, at most one, and 0. Okay. And now it's just mechanically, not much has changed. Integrate this with respect to z, you just get z, 0, 1 minus x minus y, dy dx. So this is 0 minus x, now 1 minus x minus y minus 0. I integrate this with respect to y. This is y minus xy minus y squared over 2. 2, 0, 1 minus x. X minus x plus x squared minus 1 minus x squared over 2. Plug in 0 for y, everyone 0. Let's just stop. And now integrate that with respect to x. So the integral of 1 is just x. This would be minus x squared. So it's x cubed over 3. No, minus, that would be minus 2x. So that's just minus x squared. This guy is x cubed over 3. And this guy would be 1 minus x over 6. Then I would just plug in. So I plug in 1, 1 minus 1 plus a third minus, when I plug in 0, 1 6. 1 third minus 1 6 equals 1 6. So I assume the mechanics would be fine, but does anyone have questions on how I set this up? Yeah, you do the 3D sketch of it to figure out where your 2D sketch is going to be, right? To figure out where the shadow is pointing. So you're going to decide, do I want it to go in the XY plane or the XZ plane or at either plane. Once you figure that out, then you have to figure out the limits for this guy between constants and curves, and then figure out the bottom and top surface for the third. So let's do the type 2 setup. And after this, you won't have to know the type names. I don't really care to know what's type 2 or type 3. I'm not going to ask questions in that point. Type 2 setup. So here you'd have the same guy, X, Y, Z. Boom, boom. But here I'm thinking of the projection region as being over here. Right? Which means my D is now in the YZ plane, but it still hits 1 and 1. So I can describe it very similarly. I can say Y goes from 0 to 1, and Z goes from 0 to 1 minus Y. Could do that. Also, I can figure out that my X goes between 0 to 1 minus Z minus Y. 1 minus Y minus Z. I mean, I picked a very nice solid here, so there's not much change going on. Everything's sort of generic, just switch the variables around. But in general, it won't be like that. It's that we're learning now. So here I think of the projection as being in this region. So then now this is x, z, d. So I can let x go between 0 and 1. Z goes between 0 and 1 minus x. Also your y is between 1 minus x minus z. So your triple integral is equal to 0 to 1. dy, dz, dx.
Oblivion. It's a wonderful thing. I want to live in her brain.
She was talking about math and she got lost in it, I understand. It's like, no problem. Okay. Another example. Give you guys a minute to try and set that up on your own. I was supposed to do 13.6 before this section, so it's. But 13.6 again is very short, we only need a formula from it. And 13.6 is something you're going to do in depth when you go back, for those of you going on to 392, you're going to do everything else. But for Calc 3, we only need one formula in that section. But it's a double integral formula. I was just writing in my notes, and I wrote down the notes for 12.5. I was like, damn it, forgot to do 13.6. So I'm just following my notes here. I'm like, oh, I forgot to do 13.6.
I was hoping you were skipping it.
No, it's a very short thing. Like in 13.6, we only want one formula. There's a formula for surface area that we're going to use. We're not going to do everything. Okay, how are we doing setting this up?
Well, x equals 1 is a plane.
Yeah, can you actually draw the region? Did you draw the region?
Yeah, and the other's a parabola that opens out on the x
Paraboloid.
axis. Paraboloid that opens out on the x-axis.
Yeah, so there's a paraboloid opening this way,
And then there's a plane cutting through it.
and then there's a plane cutting at x equals 1.
So the section we take would be probably the
So-
finite one rather than the infinite one, I would assume.
Yeah, it says bounded by, so
Okay.
the other part wasn't bounded. Right, so there's just this plane here. This is the plane x equals 1. This is x equals y squared plus z squared. Okay. And how do we do that integral? You want the domain where?
On the YZ side?
So you can go put the domain in the YZ. You can do that. What would it look like? It would be a circle, right? So in D, this would be y squared plus z squared equals 1, because it equals x, and x equals 1 at this point. And so for D, we can actually do the setup. We can let, say, between minus radical minus y squared plus the radical minus y squared. And x is going between what and what? No?
Y squared plus t squared.
It goes from y squared plus z squared up to 1, right? Because this is the bottom part of the solid, that's the top part, right? Sort of tilt your head so the positive x is going up, 1 is top, and this surface here is the bottom. So, a triple integral over e of y squared plus z squared, and d is just equal to 0 to minus 1 to 1 minus radical 1 minus y squared radical 1 minus y squared plus z squared up to 1.
X should be more than z squared. I think x should be more than z squared.
Huh?
I think that x should be between z squared and 1. Why is here?
X should be what?
Between z squared and 1. The last one. It's
Between z squared and 1?
Y between z squared and 1. No, x is this bottom surface here, which is the paraboloid, up to this. Right? Because the solid is this thing here, this whole thing here. Right? We're looking at this solid, where the top is x equals 1, and the bottom is x equals y squared plus z squared.
why you're looking for d, right?
Oh, you're meaning D?
Yeah.
What about D? Yeah, what about D? Remember, D is the circle in the YZ plane, right? This is Z and this is Y. Circle of radius 1. So I can solve for Z, which I would get plus or minus the radical of 1 minus y squared. Right, so I have that, and then y goes between minus 1 and 1. Okay, so how do we do that? Integrate that with respect to x, what do I get? Just x times that, right? So x times y squared plus z squared between 1 and y squared plus z squared. And z y. So this is y squared plus z squared minus y squared plus z squared. Now what do you notice about that? We could do it as a polar, right? Now, in general, we could have done it as a polar from the beginning, but that's actually the next section. We're going to do something called cylindrical coordinates. But here, we didn't have the theory to get to here yet, so we just got here manually. And now we realize that this is actually integration over a circle. We can do polar form. But now instead of x and y, I have y and z. But everything else is sort of the same. This is just, so let's do this bipolar with, let's say y equals r cosine and then z equals r sine. So that y squared plus z squared equals r squared. And so then theta goes from 0 to 2 pi, r goes from 0 to 1. This is r squared minus r to the 4th times r divided by theta.
How did you get 0 to 1 from that?
Radius goes from 0 to 1. It's a circle of radius 1.
Oh, okay, yeah.
So this is going to just be 2 pi times the integral from 0 to 1 of r cubed minus r to the 5th. It's equal to 2 pi times r to the 4th over 4 minus r to the 6th over 6. So it's 2 pi times 1 over 4 minus 1 over 6. Which is what? So that's, well, we can, the common is 12, right? So I can, this is 3 over 12 minus 2 over 12, so that's 1 over 12, right? In the next section, 12.6, we'll realize how we can jump to here from even the very beginning. But that's just some more. Just right now, I just want to mention. Oh, I think we're actually going to finish on time today. Applications. We already discussed max and centroid, which they cover in this topic, but like I said, it's just knowing the formula. The other application is volume. The volume of E. Volume of E as a triple integral is what? Again, it's just a function of 1. Just like how the double integral, that you can find the area by the double integral of 1, you can also find the volume by the double integral of 1. But you can find the volume by the triple integral of 1. Why? Let's say you had this triple integral of E of 1 dv. You could actually set this up as a double integral where it would be something like bottom surface up to a top surface. Here I'm illustrating with type 1. So this would actually give you, integral of 1 would be z, then you plug, fundamental theorem of calculus would tell you plug in the top surface, minus you plug in the bottom surface. Which was the old formula that we had for volume. Right? So triple integral of 1 always gives you volume. So our first example in this section was finding the volume of the tetrahedron. The 1d4. That's it. So homework on 12.4 and 5, and tomorrow we'll move on. Monday we'll move on.